So hello to everyone who is watching on YouTube. So I guess I'll get started with the session in a few minutes as I'm waiting for a few people to join the session. Hopefully a few of them will join. So if they don't I'll start in like 4 or 5 minutes. So yeah, I'll start in 4 or 5 minutes. Okay. Hi Shashi, I'll get started in a minute. I'm waiting for a few more people to join. So if they don't, I'll start in a minute or two. Okay, so I guess since no one is joining, I'll just start the session for the YouTube audience to follow. So yeah, hello to everyone who is watching on YouTube. Just to introduce myself, I'm Lakshya Sakhi, the Discrete Maths TA for the Tuesday sessions. So in this session, like this is the eighth session for the NPTEL course, and in this session we'll be covering problems related to graphs. Basically, there were lecture the content the questions based on last week's content, which were on introduction to graphs, handshaking lemma, matchings, and so on. So yeah, so uh, yeah, so in this session, I like usual, I have some problems prepared, and I believe this should be a shorter session because the concepts are relatively simpler since it's just an intro. The last week was just an introduction to graph. So yeah, so I guess I should get started with discussing the problems related to this week. So yeah, let me just share my screen and I'll start discussing the problems for this week. So yeah, I'm just sharing my screen. So yeah, so this I hope my screen is visible. YouTube. So yeah, so I guess I'll just start with the session. So Uh, the first question states that we have to select the graphs among the following options. So there are these four options given to us. So we have to select the graphs among the following, which have a complete matching. So among these graphs, we have to select the graphs which actually have a complete matching. So like I usually do, I like to define the preliminaries. So what is a complete matching? Maybe I should just write it again so that people get reminded, even if like this was covered in last week's sessions, but I guess still people should maybe just to remind people. So yeah. So what is a complete matching? A matching in which all the vertices of the graph, a matching in graph G is a complete matching if it matches all the vertices of G. So basically, what's a matching? We know what is a matching, so maybe I should just uh, tell you guys what a matching is also. So, okay. So what is a matching? So matching is nothing but a subset of edges of graph G such that no two edges share a common vertex. So matching is nothing but we just for a graph G, we just select a subset of edges out of that graph, and no two edges of that graph, no two edges of that subset of the subset should share a common vertex. So that's why it's sort of a matching because we every vertex can have only one edge adjacent to it. So we can sort of think of it as we are matching that vertex to to the neighbor along which the edge is selected of the matching. So yeah, something like that. So this is a matching. So and what's maybe I should reverse the order because first we should define what's a matching and then we should say what's a complete matching. So yeah. So matching is nothing but a subset of edges of graph G such that no two edges of the subset share a common vertex. And a matching is a complete matching if it matches all the vertices of G. So essentially, all the vertices are covered by some edge of that matching, and only then is it a complete matching. So yeah, hopefully the definition is clear to everyone. So now in this question, we have to select the graphs among the following which have a complete matching. So yeah. So as we can see, first of all, like all the four options are bipartite graphs. As you can see, if you remember what a bipartite graph, so bipartite graphs are, uh, maybe I should mention what a, oh, never mind. I think everyone should know what the bipartite graph is. I should not write the definition. So a bipartite graph is a graph in which the vertex set is sort of separated into two sets, A and B, such that edges can all the edges of the graph G have one endpoint in set A and other in set B. Or let's say set S1 and S2, then one endpoint in set S1, other in set S2. As we can see here in all the four options, here the graphs are bipartite because you can see if we select the vertices ABC as one set and the vertices DEF as another set, then all the edges are going from one set to another only. Basically, no edges between uh, two vertex of the same set. So like if ABC is one set, then there is no edge between A and B, B and C, or A or C. Similarly, no edge between D, E, EF and DF. That's why DEF is another set. So so intuitively, like bipartite graph is nothing but just by definition a bipartition of the graph. So yeah. So as you can see, in all the four options, it's a bipartite graph. And yeah. So we have to select the graphs which have a complete matching. So what's a complete matching? Complete matching was a matching if it covered is a complete matching if it matches all the vertices of G. So all the vertices should be covered. So maybe we should look at this option by option. So we have to select the graphs which have a complete matching. So let's go option by option here. So let's just look at all the options one at a time. So let's look at option A. So option A, as you can see here, that uh, so to show so just to decide whether it's a complete matching. So one thing we should take care is that to decide if it is a complete matching, like if we want to surely know whether it is whether the graph contains a complete matching, one way is just to output that matching, like just give one matching which covers all the vertices. And if you want to show that the graph does any graph does not have a complete matching, then we need something more refined, which is the Hall's theorem, which has which has been discussed in previous week's lectures. So I would recommend you guys, if you have not watched that, you should see the Hall's theorem and its proof, because I don't think I'll be able to cover the Hall's theorem and its proof in this session, because that in itself will take a lot of time. So yeah. So generally, like a rule of thumb is, uh, if we want to say yes that the graph has a complete matching, then we just output that matching. And if we want to say that no, the graph does not have a complete matching, just invoke Hall's theorem, and like I'll just discuss in some of the options, like how can we say whether a graph does not have a complete matching. So let's just come to option A. So in option A, it's easy to see that and there exists a complete matching. You just see consider the edge going from C to F, this C comma F edge, this B to D edge, and this A to E edge. So note that what the three edges I'm saying are this AE edge, this BD edge, and this CF edge. So it's easy to see that none of the two edges here share an endpoint. So, and all the vertices A, B, C, D, E, F are covered from these three edges. So this graph contains a complete matching. And what's the complete matching? This A, E, B, D, and C, F. So maybe I should write here that has a complete matching. And what's the matching? The matching contains the set A, E, B, D, and C, F. A comma E, then the set B comma D, then the set, then the edge C comma F. AE, BD, and CF. So these are the three edges, so it's a complete match. So let's look at option B now. So option B. So in option B, so note that we can just intuitively see that you can see these vertices B and C. Let's just see these vertices B and C. So for the this graph to have a complete matching, this C should be covered by some edge, right? And C has a degree of 1 only. So the only way this vertex C can be covered is by this edge C comma E. So this edge should be included in the matching. All if we want to have a complete matching, then this C comma E edge should be included. But note that this vertex B here, this vertex B also has only one edge going out of it. So if it is, since all vertices need to be covered, so vertices B and C both need to be covered by the matching if we want to have a complete matching. So if the graph contains a complete matching, then C should be covered by the C comma E edge. Similarly, this B can only be covered by this B comma E edge. So basically, if the graph contained a complete if this graph contained a complete matching, then C comma E should have been a part of that matching. And similarly, this B comma E should also have been a part of that matching. But note that this is not possible because in a matching, as we defined the matching, in a matching, no two edges should share a common vertex. So here we can see if the complete matching has this B comma E edge and this C comma E edge, then E is a shared vertex. So that's how basically intuitively you can see that this graph will not have a, a complete matching. So option B does not have a complete matching. Have a complete matching. So I'll just come back. I want to, I'll just write the reasoning for this also, but I want to come back to this later, like after I've covered all the options, because I want to discuss Hall's theorem at the end of this question discussion. So yeah, so let's just see option C now. So in option C, you can clearly see that it contains a complete matching. And what's the matching? This A to D, this B to E, and this C to FH. So these three edges you can see form a matching and all the vertices are covered. So that's why it's a complete matching. So option C has a complete matching. Maybe I'll just copy and change the values of the edges. So the first edge is A comma D, second edge is B comma E, third edge is C comma F. So yeah. So now let's go to option D then. So in option D, again, a very similar situation to option B arises if you see if you see closely. In option B also we saw that these vertices B and C had degree 1. So these two edges had to be present in the complete matching. And that's why the graph did not contain a complete matching. Similarly, in option D here, what we can easily see is again this vertex C has a degree of 1. So this C comma DH should be present in the matching. And similarly here, this vertex B also has a single edge. So this B comma D should also be part of complete matching. But note that B comma D and C comma D, both of these edges cannot be part of a matching because uh, a matching, the edges selected in the matching should not share any vertex. So yeah, maybe I should now just write down the reason for option B, like why does option B not have a complete matching? So suppose it had a complete matching. Then basically vertices B and C should also be covered by the matching. Matched by the matching or covered by the matching, we can say anything, like it's just notation. So yeah. So vertices B and C should also be covered by the matching. Uh, but since so so we established that vertices B and C should also be covered by the matching. As B and C both have a degree of 1, they can only be covered by the edges. So B can be covered only by the edge B comma E. So B can only be covered by B comma E, and the C can only be covered by C comma E. So B comma E and C comma E respectively. So B can be covered only by B comma E and C can only be covered by C comma E. So both B comma E and C comma E should be part of the complete matching, which is a contradiction, as a matching as basically two edges of a matching. So why is it a contradiction? As I explained earlier also that the if we select these two edges B comma E and C comma E, then E is a common vertex. But no two edges of a matching should contain a common vertex. So that's what I'm writing. So as two edges of a matching, sorry for this. Cannot share a common vertex. So I guess something like it is clear. So like again, like it had a complete matching, so I just output the matching in option A and C. But if the graph did not have a complete matching, so I need to be sure of this fact, right? That the graph does not have a complete matching. Maybe what happened was the graph indeed contained a matching, but my eyes were not able to catch it. So that's why, just to be sure, we should have a proof in hand that we can be sure that the graph does not have a complete matching. So yeah, so that's why we can sort of say that two edges of a matching cannot share a common vertex, and that's why this graph won't contain a matching. So similar arguments will apply in option D also as the option B. So it does not have a complete matching. And why does it not have a complete matching? I just write similar argument to option B. So in option D also we had similar argument that B and C have a degree of 1. So this B comma D edge and C comma D edge should be present in the complete matching. But this is a contradiction as in that case D would be a shared vertex in the matching, which is not possible. So yeah. So that's why option B and option D do not have a complete matching. So So these sorts of reasonings of this type, like suppose you have a complete matching and stuff like this, and why does it not have a complete matching? Here we use some reasoning of degree 1, degree 1 vertices, right? But sometimes degree of vertices can be larger also, and then using these sorts of argument can become difficult. So that's why in last week, I hopefully you guys would have covered the Hall's theorem. Maybe I should write this in bold or like, I don't know. I should underline this. Alternate, or this is not an alternate, but rather a better way to prove that the graph that a bipartite graph does not contain a complete matching. So basically, a better way to prove that a bipartite graph does not contain a complete matching is using Hall's theorem. So I would recommend you guys to look it up because this has been covered in lectures, and this is like Hall's theorem is one of the most fundamental theorems in graph theory. So if one is studying graphs, like one should definitely know about this theorem. So yeah, it is an important theorem. So using Hall's theorem, so basically, just to give you, should I describe? I guess I should not describe because like if you go through Hall's theorem in from the lectures, then like it would have been clear anyway that why this set of B comma C will form something like what is called an Hall set, and it will ensure that and that's how we can say that this graph won't have a perfect matching. So in option B and D, like if you already know what the Hall theorem is and what Hall set is, then for that audience, I'm just saying that how we can say that option B does not have a complete matching. This the vertex set of B comma C actually forms a Hall set. And what do I mean by the Hall set? So basically, this B comma C is a subset of two vertices, but its neighboring subset of vertices contains only the set E. So cardinality of set S is greater than cardinality of its neighboring set. So neighboring set is only set E, which is only one vertex, but the actual set had two vertices. So this was something which you can identify as a Hall set, or like if you have already seen the Hall theorem videos, then you can see that like you can sort of all see that this B comma C set is the reason why like Hall theorem fails, and that's why this graph does not have a complete matching. So similarly here, the vertices B and C, they'll form a Hall set here because this is a vertex set of size 2, but the outgoing vertex set size has only the vertex D in it. So again, cardinality of this B comma C set is greater than the cardinality of its neighboring vertex set, which contains only D. So that's why, again here, this is a Hall set, which proves that this graph won't have a complete matching. So yeah. So yeah. Also, this is all sort of an alternate or better way because like this sort of reasoning of complete matching and degrees and stuff like that is easy for smaller size graph, but for larger size graph, I believe giving a Hall set or using the Hall theorem is a much more cleaner way. Although this is also somewhat of a generalization of these sorts of arguments, but yeah, I feel that it's a lot cleaner. So that's why I'll recommend that you should use Hall theorem. So yeah. So then coming to, I guess, question 2. Uh, so in the second question, so what's the second question? So second question defines, so consider the following values. So basically, second question defines four sorts of values, n1, n2, n3, n4 as like some values given according to some statements, like n1 is number of graphs in this set, or n2 is something, something, something. And then we have to sort of find out the value of n1 plus n2 plus n3 plus n4. So effectively, like this is just with the finding out the value of n1 plus n2 plus n3 and n4 is essentially like saying we need to find out what's the value of n1, what's the value of n2, n3, and n4 separately, and then we can just output their sum. So yeah, this is not the important part. Finding out what are the values of n1, n2, n3, n4 here is the important part. So let's just see. We'll calculate the values of n1, n2, n3, n4, n1, n2, n3, n4 separately. So now first let's just calculate the value of n1. So what's n1? N1 is the number of graphs in the set K3, W3, Q3, and K13, which have equal vertex and edge connectivity. So first of all, uh, this concept of vertex connectivity and edge connectivity, like you should be knowing because this was also covered in the lectures, but maybe I can remind you guys about the definition of this. So first of all, so what's a vertex connectivity and what's an edge connectivity? So let me just explain. So edge connectivity of graph G. So what is intuitively edge connectivity of a graph G? So edge connectivity is nothing but uh, it essentially say edge connectivity essentially says like what's the minimum number of edges which we need to remove from the graph. So like of a connected graph, let's just say it's a connected graph. So these connectivity arguments are defined for connected graphs only. And what's a connect? So this is not connectivity, but connected graph. And so what's a connected graph? A graph in which there's a path between every pair of vertices. That's a connected graph. So this definition you must know. So what is edge connectivity of a connected graph? Edge connectivity of a connected graph, nothing but the minimum number of edges which we need to remove from the graph so that the graph becomes disconnected. So what's the edge connectivity? Minimum subset of edges which need to be deleted from the graph, or like let's say from G, so that G become disconnected. So essentially what it's saying is that so initially we are given a connected graph G. So it's trivial that to make it disconnected, we can just remove all the edges of that graph. Let's say it had some 100 edges, then we could have removed all the 100 edges of that graph. And now the graph is easily, as you can see, disconnected because each of the component now consists of a single vertex only. But like that's not the like, so we can always disconnect a graph by deleting edges, right? So now what an edge connectivity says is that we want to find out the minimum subset of such edges. So minimum size, maybe minimum size. So basically we want to say that we want to find out the subset of minimum cardinality, or let's say minimum size of of the edges which should be deleted from G so that G becomes disconnected. So there can be multiple subsets of edges which when deleted make G disconnected. But what we want to find out is the minimum size such subset, right? So similarly, what's the vertex connectivity of a, these connectivity things are only defined for connected graphs, first of all. Similarly, now let's just come to vertex connectivity. So what's vertex connectivity? It's similar to its connectivity, just now we need to, as you can see from the definition, it must be that we just need to delete the vertices. So minimum size subset of vertices which need to be deleted from G so that G becomes disconnected. I guess This is these definitions should be pretty easy to follow. If you still don't understand, maybe you should refer to lectures because these definitions have been covered in the lectures. So yeah, so if these definitions are clear, then we can sort of proceed to calculating these values of n1, n2, n3, and n4. So, so n1 is nothing but the number of graphs out of this set k3, w3, q3, and k13. So we are given these four graphs. So, and out of these four graphs, we have to find the number of graphs which have equal vertex and edge connectivity. So we have to basically verify for all of these four graphs if they have equal vertex and edge connectivity. So this is a sub problem in itself. So for K3, we have to identify whether what's the vertex connectivity and what's the edge connectivity and see if they are equal or not. Similarly for W3, similarly for Q3, and similarly for K13. So what's K3, what's W3, Q3, what are these notations? So these notations have also been covered in graph in the class, but I'll just show you these graphs again. Like what are these graphs? So let's just see first of all this K3 graph. So we are given these four graphs K3, W3, Q3, and K13, and one by one we'll see all these four graphs and see which of these graphs have equal vertex and edge connectivity. So yeah, and that's how we'll calculate N1. So let me just show you the K3 graph. So yeah, so this is the K3 graph. So in K3 graph, it can easily be seen that so these say K3 graph is nothing but basically a complete graph on three vertices. So these are the three vertices, the green dots, and here are the three edges. So now we sort of need to see whether it has equal vertex and edge connectivities. So to see that, we just see first of all what's the vertex connectivity of this graph. So it can be easily seen here that even if we delete one word, if we delete this, let's say the topmost vertex, the remaining graph still remains connected, right? Or maybe, yeah. Okay, so I just want to point out something. So edge connectivity is the minimum size subset of edges which need to be deleted from G, so that remaining part of G, remaining part of G becomes disconnected. And or maybe I should just stay with this definition. I don't think there's any issue with this. So never mind. So maybe we should keep this definition as it is and just see here. So here, first of all, let's say in this K3 graph, I want to find out the vertex connectivity. So I need to find out the minimum number of vertices which I need to delete so that this graph becomes sort of disconnected. So you can sort of see that if we delete this topmost vertex, still these bottom two vertices will remain connected, even if this topmost vertex is deleted. So deleting a vertex means deleting its neighboring edges also. So these two edges are deleted and this vertex after deletion of this vertex, but still the remaining two vertices remain connected. So after that, if we remove another vertex, so if we remove another vertex after this, so if these two vertices are removed, then these edges, all three edges are also removed by that. So only a single vertex remains. And a single vertex without any edges is also a connected graph because it's a connected component, let's say. So even after two deletions, this graph does not become disconnected. So if we delete all the three vertices, then there is no graph remaining. And generally in vertex connectivity, it's defined that if we need to remove all the vertices, then this means that the vertex connectivity is actually equal to like the size of the vertex set. So let me just confirm this. So yeah. So sorry for the delay. So what I just want to point out here was, so yeah. So we are deleting these three vertices, and after that, no vertex of the graph remains, right? So that sort of, if there is no graph remaining, then it is sort of a disconnected graph because there is nothing remaining. The vertex set and the edge set is empty. So that's why we'll sort of say that vertex connectivity of K3 will be equal to 3. So in for while calculating N1, we'll first see the graph K3. So maybe I should put these in bullets. Or no, or yeah, maybe I can. So yeah. So so while calculating the value of K3, we sort of know that for K3 vertex connectivity is equal to 3, because after deleting all these three vertices, we'll be left with no, like, vertex connectivity is definitely not 2, because after deletion of two vertices, still a single vertex remains, and this single vertex is one vertex connected. So yeah. So that's why we need to remove all the three vertices. That's why its vertex connectivity is 3. Now, similarly, we need to find out edge connectivity of this K3 graph. So we need to find out what's the edge connectivity of this K3 graph. So for viewing edge connectivity, edge connectivity can also be seen here that if we remove any one edge, still the remaining graph is connected. Like, just remove this left side edge of the triangle, still the graph remains connected via the straight line. So we'll sort of need to remove another edge. So we'll need to remove two edges to make the graph disconnected, right? The left one and this right one. So after deleting these two edges, the graph becomes disconnected. So is this clear? Like, obviously, so there's no one in the meeting. I guess the one person who was there has left. So yeah. So so after deleting these two vertices, this vertex becomes disconnected from these two vertices. So that's why we can sort of say that deleting these two edges makes the graph disconnected, and so the edge connectivity of the graph is actually equal to 2 only, because after deletion of like these two edges, like after deletion of any single edge, the graph trivial remains connected. But after deletion of these two edges, it becomes disconnected, as this vertex and this set are disconnected now. So edge connectivity is 2 here. So similarly, first we did this for K3, right? Now we need to sort of uh, do this for the second vertex W3 also. The second graph W3 also. So for the graph W3, so for this graph W3, so what's a W3 graph? I'll also show you what's a W3 graph. So W3 graph is uh, nothing but what's called a wheel graph. And I'll just show you its image. So yeah, okay, the image is a bit blurry. I don't know why, but yeah. So this is what's called a W3 graph. So even though the image is blurry, you get the idea, right? That there's this triangle, and at the center of this triangle, there is another vertex, and which is connected to all the three vertices of this triangle. So that's why it's sort of forming a wheel. And that's why it's called a wheel graph, and hence the notation W3, because wheel starts with a W. So yeah. So here we need to find out again the vertex connectivity. So what will be the vertex connectivity here? So note that again, it can be seen that deleting any single vertex won't make the graph disconnected, because if we delete any one vertex, the remaining graph, like let's just say I delete this topmost vertex, the remaining graph is a triangle graph, so it still remains connected. So we definitely know that deleting only one vertex won't make it disconnected. And maybe you can see that even after delete, if we delete, let's just say the center, let's just say I delete the center vertex. If I delete the center vertex, then after deleting this, only the triangle graph remains. And as we have previously seen that in a triangle graph also, uh, in a triangle graph, we need to delete all the vertices to make it sort of a disconnected graph, right? So after deleting the middle vertex, we'll still need to delete all the three vertices to make it an empty graph. So we'll sort of need to delete all the four vertices here to make it a sort of a disjoint graph. So that's why here we'll say something like that vertex connectivity is actually equal to 4 here, because we'll need to delete four vertices, all the four vertices here. And what's the edge connectivity? So I think there's a slide. I also have a slight confusion. Maybe I'll just discover it myself and will inform you guys. So for edge connectivity, you can clearly see like the minimum number of edges which we need to remove so that the graph becomes disconnected. Let's just say we remove all these top three edges. The top three edges of this graph, like originating from uh, this center, or let's just say we just take the central point and delete all the three edges originating from it, right? Then what this implies is that this central vertex gets sort of disconnected from all these three vertices. From all the remaining three vertices, this central vertex gets disconnected. So we need to just to delete these three edges, and it became sort of disconnected. So that's why it is sort of edge connectivity is equal to 3, because after deleting three edges, we were able to obtain. Okay, then we just go to Q3. So what's Q3? Uh, Q3 is again a graph which is called something like cube graph. I'll show you what a Q3 is. Okay, so this is what is called a Q3 graph. So it's sort of Q, like basically 8 vertices. So you can see this forms actually sort of a cube, something like a cube. So that's why it's called a Q3. And Q, even though Q starts with a C, not a Q, but C symbol is of a cycle. So that's why they start this Q by a Q. So yeah, so this is the Q3 graph. And now in this Q3 graph, we'll again need to find out what's the vertex connectivity. So yeah. So here to find out what's the vertex connectivity, let's just say I just delete this edge, this vertex here. Uh, the vertex on which my on which my cursor is present. So if I delete this vertex, you can still see that the remaining graph will still be connected because there'll be a path from every vertex to every vertex in the remaining vertex set. So at least we know that vertex connectivity is not one. But let's say after deleting this vertex, uh, what other vertex I delete? I delete something like, let's say, uh, yeah. So maybe what can I delete? So let's just say I take this vertex and delete all its neighboring vertices. I take this vertex on which my cursor is present and delete all its neighboring vertices. So this vertex is deleted. So this vertex is deleted. This vertex is deleted, and this vertex is deleted. So these three vertices are deleted. So you can see corresponding that these three edges will also get deleted. So this vertex got deleted, this vertex got deleted, this vertex got deleted. So after deleting these three vertices, uh, this vertex becomes isolated from rest of the graph. Like this graph still remains, but this vertex here becomes isolated. So that's why we sort of know that deleting three vertices at most will do the trick. And we know that deleting one vertex won't do the trick. We just need to verify whether deleting two vertices also can make it disconnected or not. But I believe even after deleting two vertices, we won't be able to obtain a disconnected graph because let's say the first vertex deleted was this vertex, then you can sort of see that deleting any other vertex, if we delete any other vertex also, still the graph would remain connected. So like it's sort of easy to see. You can verify this yourself also that deleting only two vertices won't do the trick. So we'll have to sort of delete three vertices at least. So that's why here we'll say that vertex connectivity is three. And as for edge connectivity, so for edge connectivity, we can use similar arguments as we use for vertex connectivity. So for this vertex, we can just see its outgoing edges. There are three outgoing edges or three neighboring edges. So if we just delete these three edges, then the graph becomes disconnected because this vertex again gets isolated from the rest of the graph. And it's easy to see here that again, where you can verify this yourself also that deleting anything less than three edges won't do the trick. So what edge connectivity is also three here. And now let's come to the fourth graph, which was this K13 graph. So this graph called K13. So this K13 graph, I'll show you this graph also. What's this graph? It's like so. This is what you call a K13 graph. I'll just label it here. So this graph is what you call a K13 graph. So basically one vertex and three vertices having edges to it. So this is a K13 graph. So as you can see here, in this K13 graph, if we need to find out what's the vertex connectivity, uh, then it's easy to see that deleting this vertex 1, if I just delete this single vertex 1, then these 2, 3, and 4 vertices become disconnected, right? Because now there is no path from 2 to 3, 3 to 4, and 2 to 4. These will become singleton components. So that's why vertex connectivity is 1 here. Note that I could have also deleted the single vertex of, let's say, this vertex 2, but then the remaining set would still be connected. So that's why, and we need to sort of find out the minimum sized vertex set. So this vertex 1 is the minimum size such set, which sort of disconnects this 2, 3, and 4. So after deleting this vertex 1, we'll be left with these vertices 2, 3, and 4 component. So that's why its vertex connectivity is 1. And similarly for the edge connectivity, we can also see that we can delete any of one such edge. Like let's say I just delete this 1, 2 edge. After deleting this edge of 1, 2, and this vertex 2 gets separated from the component of 1, 3, 4. So essentially the graph becomes disconnected. So yeah, so that's why even after deleting one edge, the graph becomes disconnected. So edge connectivity is 1 here. So yeah, so as we can see here that in this graph vertex connectivity is 1 and edge connectivity is 1. So yeah. So, so we see that while calculating the value of n1, so for n1, we need to find out the number of graphs in this set which have equal vertex and edge connectivity. So first graph has edge connectivity of 2 and vertex connectivity of 3. So it does not contribute. Second graph has 4 and 3, so it does not contribute. So similarly, third graph has both vertex connectivity of 3 and edge connectivity of 3. So it contributes. Similarly, the fourth graph has vertex connectivity of 1 and edge connectivity of 1. So this also contributes. So yeah, so there are these four, there are these two graphs Q3 and K13, which satisfy this property of having equal vertex and edge connectivity. So yeah. So yeah. So one thing I think I have missed out on is so yeah, one thing which I missed out on is the definition of vertex connectivity, like the definition of vertex connectivity which I discussed here, that minimum size subset of vertices which need to be deleted so that G becomes disconnected. From this definition, we would obtain the vertex connectivity as this 3 and 4 for these graphs and this 3 and 1. But there is a slight, I believe there has been some, I've missed something, which is that vertex connectivity is essentially minimum size subset of vertices which need to be deleted so that G becomes disconnected. So this is one criteria, or the other criteria is or G contains only a single vertex after deletions. So essentially what I'm trying to say here is that so how do we define vertex connectivity? So minimum size subset of vertices which need to be deleted from G so that G becomes disconnected. So this was the definition which I was following for now. But I believe like I sort of realized that this definition is sort of incomplete for vertex connectivity. For edge connectivity, this definition is correct. Just deleting the edges so that graph G becomes disconnected. But for the vertex connectivity, the definition is the minimum size subset of vertices which need to be deleted so that G becomes disconnected. Either this happens or G contains only a single vertex after deletion of vertices. So what it means is that suppose I had deleted, there were n vertices and I had deleted n minus 1 vertices, then I will be left with only a single vertex, right? So in that graph, vertex connectivity would, even though single vertex is not disconnected in itself because a single vertex is also a connected component, but still we would say that if we are left with a single vertex, then that the vertex connectivity of that graph, initial graph, is n minus 1 and not n. So even if we are left with single vertex, we'll sort of think of it as a disconnected component. That's what I'm sort of trying to say. So vertex connectivity can never be greater than n minus 1. So because after n minus 1 deletions, we'll be left with only a single vertex, and so a single vertex. So yeah, so it will satisfy that definition of vertex connectivity. So yeah, so I guess there'll be some changes here. Apologies for that. So Following that definition, so here we see that in K3, I had defined vertex connectivity as 3. But note that since like K3 has 3 vertices and I have already told that vertex connectivity cannot be greater than n minus 1. So it should have a maximum value of 2. And why will it have a maximum value of 2? Because you can see that if I delete this vertex and I delete this vertex in K3, then I'm just left with a single vertex. And if we are left with a single vertex, then also it satisfies the definition as we discussed in vertex connectivity. So effectively, vertex connectivity is not 3, but 2 here instead. Because after deleting 2 vertices, I'm left with a singleton vertex. Similarly, in this graph W3, I had defined this as vertex connectivity as 4. But if I just delete 3 vertices here, then I'll be left with a single vertex. So here vertex connectivity is 3 and not 4 actually. In terms of the previous definition which I was discussing, which was in terms of disconnections only, if we just followed that definition, then vertex connectivity would have been 3 and 4 in K3 and W3 respectively. But like that is not the correct definition sort of. We need to take the second condition also into account, which is that the remaining graph, if the remaining graph is a singleton vertex, then also we consider it in vertex connectivity. So yeah. So these two things will change, although these two things will not change because you can see that here vertex connectivity was 3 and number of vertices was sort of 8. So it does not so vertex connectivity is not exceeding n minus 1 here. Similarly in K13 also vertex connectivity is not exceeding n minus 1. So these two were correct. But these two are incorrect. Also, and these two were earlier incorrect, but now they are correct. So yeah. So now we see sort of that the number of graphs in this set which have equal vertex and edge connectivity are essentially like all the graphs have equal vertex and edge connectivity. Okay, so Azhar Gurusu has joined the meet. Oh, so hello Azhar. So this is sort of second question which I'm discussing for today. And here, so you're asking, so Azhar is asking what is Q3? So Q3 is this graph. Like I have written down, I have pasted all the pictures of all the possible graphs, which are these. So yeah. So as you can see, like this is so there is this 4 graph, which I'm considering the K3 graph is this graph. W3 is this graph, even though it's a bit blurry. This Q3 is this graph. So note that why are these named like this K3, Q3 and stuff like this? So this W refers to sort of this W means a wheel graph essentially. So as you can see here that this looks like a wheel, right? That's why it's called like it starts with a W. Similarly, this is called Q3 because this sort of looks like a cube. So cube, the spelling of cube, even though spelling of cube starts with the C, but C is reserved generally for cycles in graphs. So that's why they call this a Q graph. So it starts with a Q and Q3 because it's a like 3-dimensional structure. So yeah, so this is the Q3 graph. And this is the W3 graph. Like a triangle with a vertex in the middle, which has 3 edges to all the corners of the triangle. So I hope this resolves your query, Azhar. So this is the definition for Q3 and W3 and so on. So let's just go to, I guess, the so we calculated this N1 here. So basically, what's the value of N1 here? So N1 is essentially equal to 4 because all the 4 graphs have vertex connectivity equal to edge connectivity. Right. Now let's go to calculating the value of N2. So N2 is nothing but it's saying the now let's just maybe yeah. So maybe I should calculate the value of N2 after all these diagrams. Otherwise, it can become confusing. So yeah. Or maybe I should copy this diagram of this thing. Yeah, I guess this should. Mm. So now we had calculated N1 and now we calculate. So now we calculate the value of N2 and what's N2 defined here. So N2 is the degree of each vertex in G prime, which is complement of a regular graph with 6 vertices, each having degree 3. So if you have seen the lecture, so what's a regular graph? A regular graph is a graph in which every vertex has equal degree. So all the vertices in which all the vertices have same degree basically. So basically in this regular graph G, it's given that we have 6 vertices and all the vertices have a degree of 3. And note that so basically N2 is the degree of each vertex in the complement of the regular graph. So note that what's a complement of a graph? So complement of a graph is nothing but a graph in which all the edges which were present in the initial graph are not present and vice versa. So basically to create make a complement of a graph, what we essentially do is um, make a graph G prime and add all the edges which are not present in G and don't add the edges which are actually present in G. So that's how we obtain a complement of a graph. So we need to find the degree of each vertex in G prime, which is complement of the graph G. So note that it's easy to see that in this regular graph G, there are 6 vertices and all the vertices have a degree of 3. So let's just consider any vertex V. So as there are 6 vertices of the graph, 6 vertices in the graph, so except V, there will be 5 more vertices, right? So and V has edges to 3 of those vertices. So V has edges to 3 of those vertices out of the 5 vertices. So V does not have edge to 2 vertices, right? There are 5 vertices except V, and V has edges to 3 of them. So V does not have an edge to 2 of them. So in the complement graph, V will have an edge to these 2 vertices instead. So that's why in the complement graph, the vertex V will have a degree of 2. So maybe I should write it down also. Consider any vertex V in G. Then V, there are 5 more vertices in G except V. And V has edges to 3 of them in G. So V does not have edges to 2 of those vertices. Hence, V will have edges to these 2 vertices in G prime. So G prime is just the complement graph. So in complement graph, we add the edges which are not initially present and don't add the edges which were initially present. So we will have edges to the vertices to which the edges were initially not present. So there were 2 such vertices into which edges were not present. So in G prime, we will have edges to these 2 vertices. So degree of V will be equal to 2 here. And since like this argument will apply to every vertex, since this was a regular graph, so every vertex initially had edges to 3 of the vertices. So now it will only have edges to 2 of the vertices. So this is why N2 will be equal to 2. N2 was actually nothing but the degree of each vertex in G prime, which was complement of graph G. So G had degree of 3, G prime will have a degree of 2. So note that G prime will also be a regular graph. And as in G prime also, every vertex has equal degree, which is 2. Even though the degree 2 is not equal to degree 3, but yeah, it's a regular graph for you. So now, now we need to see what's the value of N3. So N3 is defined as number of edges in a simple graph with 4 vertices, each having a degree of 3. So this is sort of easy because so basically we need to say we need to find out the number of edges in a graph which has 4 vertices and each vertex has a degree of 3. So we saw this is a very common property and must have seen the lectures also that summation of degrees of all vertices is equal to twice the number of edges. So I'll write it down also. I'm just discussing this only for now. So summation of degrees over all vertices here will be there are 4 vertices and each has a degree of 3. So summation of degrees over all vertices will be 4 times 3, which is 12. And we know that this is actually equal to 2 times the number of edges in the graph. And this is a very simple property. So from this, we sort of obtain that 12 is equal to 2 times number of edges. So number of edges will actually be equal to 6 here. I should write it down also. So how to calculate N3? So N3, sum of degrees over all vertices is actually equal to 2 times number of edges. So if E is the edge set, then this mod E denotes the cardinality of that edge set, effectively meaning the number of edges of that edge set. So this implies that so this implies that sum of degrees over all vertices. So the vertices, there were 4 vertices and all had degree 3. So sum this side sum will be 4 times 3. So 4 times 3 is actually equal to 2 times number of edges. And this gives us that like this number of edges is actually equal to 6. So hence N3 is equal to 6. So similarly coming to N4, now, minimum size of maximal matching in C7. So what is C7? So again, I'll just show you guys what C7 graph is. C7 is nothing but a cycle on 7 vertices, but nonetheless, I guess I should show. So yeah, so this is a C7 graph. So yeah. So although the numbering is a bit wonky, like you can just consider numbering as 1, 2, 3, 4, 5, 6, 7, or I have just like the image which I have shown here consists of numbering of, let's say 1, 2, 3, 4 in this manner. It doesn't matter how you number the vertices, but essentially C7 is nothing but a cycle of 7 vertices. And now they sort of want to find the minimum size of maximal matching. So maximal matching must have also been discussed in the lectures. So maximal matches is nothing but a matching in which no further edge can be added to extend the matching. So maybe I should write down this definition also. Maybe, yeah. Some maximal matching. A matching in which further edge can be added. So matching is just a subset of edges. And now a maximal matching is a subset of edges. So basically it's a matching in which no further edge can be added to increase the size of the matching. So basically, if we are given a subset of edges such that we cannot add any more edges to that subset, otherwise it will break down the matching property that every vertex should be covered only once. So this type of matching is called a maximal matching. So yeah, a matching in which no further edge can be added to increase the size of the match. So yeah. So now in this question, in N4, we need to calculate the minimum size of maximal matching. So there can be multiple maximal matchings in a graph, and we sort of want to find the maximal matching of minimum possible size. So now as can be seen here, like let's just say we just include this edge of 1,6 in the matching. Like in maximal matching, let's say my edge of 1,6 was included. Like this figure is symmetric, so if at least one edge was included, let's just say this 1,6 was included. So now one sort of maximal matching which I can see here is I add this edge 1,6, I add this edge 4,2, and this edge of 3,5. So note that what edges I am adding here 1,6, 4,2, and 3,5. So now you can sort of see that no further edge can be added to this matching because this edge cannot be added because it shares endpoint with 1 and 3. Similarly, this edge can't be added. Similarly, these two edges also can't be added. So we sort of know that we have obtained a maximal matching of size 3. And we need to sort of find the minimum possible size maximal matching. So anything which is less than 3 is 2. So the main problem now lies in finding whether there exists a maximal matching of size 2 here. So the answer is there does not exist any maximal matching of size 2 here. It can be seen easily here because if I have any one edge selected, like the figure is symmetric, so I can select any one edge. And if I select any other edge, let's say after 1,6, I add 2,4, then there is possibility of adding 3,5 also. So after 2,4, it won't be maximal with size 2. So I can't add this 2,4 edge if I want to obtain a matching of size 2. Similarly, adding this edge of 2,7, still I can add this edge of 3,5. And now if I instead add this edge of 7,5, I can still add this edge of 2,4. So you can easily verify that for all possible choices of size 2 matchings, none of them will be maximum. So the maximal matching will be of size 3 only here. Like the minimum possible size will be size 3 only. So that's why. So I'll just give an example. So minimum size, maximal matching. And what's the matching? I'll just give out the edges of that matching. So there can be multiple such matching. I'm just writing one of them. So it contains the edge 1,6, then this edge 4,2, and then this edge of 3,5. So the size will be 3 here, like the matching has 3 edges, so size of matching is 3. So hence the value of N4 is actually equal to 3. So we obtained that N3 was 6. Is this underline or maybe not? Let's bold these. N3 was 6, N4 was 3, N2 was 2, and N1 was 4. So from here, what do we obtain? The value of N1, N2, N3, and N4. The sum of N1 plus N2 plus N3 plus N4 will be equal to 4 plus 2 plus 6 plus 3. which will be 6 plus 6, 12 plus 3, 15. So the answer will be 15. So hence n1 plus n2 plus n3 plus n4 is actually equal to 15. So yeah. So this is the final answer. So this is the final answer to the question. Okay. So now let's come to question 3 then. So question 3 is saying that let G be a simple connected graph where every vertex has even degree. And now consider a vertex V, which so G is a graph which has every vertex has even degree vertex. And now if we consider any vertex V which has a degree of 2D, so like this 2D is just to make sure that it's an even degree vertex. So now what can be said about number of components in the graph G minus V obtained after removing the vertex V? So let's say G was initially a graph given to us, and now it had a vertex V which had a degree of 2D. So now we want to sort of say that uh, what will be the range of, like, let's say the number of components in the graph of G minus V. So if we delete the vertex V, so the graph G can break into multiple components, right? So we sort of want to say, we want to argue like in how many components can this graph G actually break after deletion of V. So note that someone a very trivial bound here would be like, since V has a degree of 2D, so maybe there were 2D components connected to V, 2D independent components which were connected to V. So if we delete the vertex V, then like at max 2D components can be obtained, 2 times G, because 2 times D is the degree. So one trivial upper bound is 2D. One trivial upper bound for number of components in G minus V is 2D, as we can have 2D edges acting as so as V has sort of, maybe I should just write as V has 2D edges and each edge may be connecting V to one of the components. So basically V has 2D edges and each of those edges can be connecting V to one of the components. So that's why sort of the number of components will have an upper bound of 2D in the graph G minus V. So yeah, I hope this is sort of clear. Another way to look at it is maybe by using something like contradiction. So like, let's just say after deleting the graph and deleting the edge V, we have more than 2D components in the graph. Then what this essentially means is that earlier the graph was connected, like G was given to be a connected graph initially, but now we have more than 2D components after the deletion of V. So it means that see, each of those components must have been earlier connected to V. And that's why after deletion of V, these components became disconnected. Otherwise, they can't become disconnected. So that's why and for each component being connected to V, there must be an edge from that component to V, right? And there can be only 2D such edges. So there can be only 2D such components at max. So one thing we can say for sure is for any graph, uh, there can only be 2D components maximum. But note that we are not given any graph. G is a simple, we are not given any connected graph. We are given a connected graph where every vertex has even degree. So like because of this even degree, like what I'm trying to say is we can improve this 2D bound even further. We can improve this 2D bound even further. Like we can reduce it. Like improving an upper bound is essentially saying that we can reduce that upper bound's value. So it's given to us that in this graph, the number of components can be 2D. But if the graph if in this graph every vertex has an even degree, then I'm claiming that like every vertex of G has even degree, then number of components in G minus V will be less than equal to D actually. So actually the answer will be it cannot exceed D. And why will this be the case? So this will be the case because why will this be the case that if every vertex of G has even degree, then number of components in G minus V is less than equal to D. So just to give you an idea of why will this be the case. So deleting a vertex, like I'll just explain it in high level for now and I'll just write it down afterwards. So deleting a vertex is essentially deleting all the neighboring edges of that vertex. Right? I can think of it as like deleting all the edges which are adjacent to that vertex. And now this vertex is isolated and I can just put it away. So essentially what I'm saying is uh, after deleting uh, all the neighboring edges of that vertex, like I'll be left with the desired number of components. So uh, earlier what I was trying to say was that these edges, these 2D edges can be connected to 2D different components. But now what we'll show is if every vertex has even degree, then at least two edges must be connected to each of the components. So like earlier I was saying that there were 2D components and each of the components uh, should have had an edge to V. So should have had one edge to V at least. So this means that every component, so there can only be 2D components. But now what I'm trying to claim is if every vertex has even degree, then all of the components of G minus V must have at least two edges to V instead of one edge. So maybe I should write it down a bit to make it. So as V has today, two and each edge may be connecting V to one of the components. So uh, each of the components of C minus V, like this was the claim and this is the reason that why is this that here the number of components will be less than equal to D. In any general graph, it will be less than equal to 2D. But if every vertex has even degree, this special property, then number of components will be less than equal to D. And why is this the case? Because each of the components of G minus V uh, will have at least two edges to V. Like uh, so like each of the components G minus V will have at least two edges like adjacent to V, or let's say two edges will be there which connect that component to V. So, and why is this the case? This is because like, so for this, we to prove this claim, we'll sort. So first of all, like, if this is true, like let's say each of the component will have at least 2D, it will have at least two edges to V, uh, then this sort of claim is easy to justify, right? Because if each of the component has at least two edges to V, and V only has 2D edges, then we can sort of say there can only be like there are 2D edges and at least two edges will be like adjacent to one component. So the maximum number of components which can be there are D only. So number of components. So the or maybe the number of components will be less than equal to D. Yeah. Maybe I should write it as claim 1 and this is claim 2. So basically, like if this claim 2 is true, that each of the components will have at least two edges to V, like let's just say I call this claim 2. Uh, so what I'm trying to say is I claim this and then I claim this. And what I'm trying to say is this claim proves this. Or maybe I should write it down in reverse order so that it becomes a bit more comprehensible. I can call this the claim 1 and this the claim 2. So yeah. So what I'm trying to say here is that I have not given the claim once proof or reason. I have not given claim once proof that each of the components will have at least two edges to V. But let's just assume this claim 1 was true. If claim 1 was true, then I can confidently say that claim 2 will be true. And why is this the case? As V has only 2D edges, number of components will be V has only 2D edges and each component of G minus V has greater than equal to two edges incident to V. And why is this true? This is by claim 1. So the number of components will be less than equal to D. So this is straightforward maths. So the only thing which we sort of need to show is that uh, the proof for claim 1, that if claim 1 is true, then this claim is true, that number of components will be less than equal to D. So I hope this is clear to everyone. If it is not, like, you can sort of go through the recording again, go through the video again, or sort of try to read up this write-up, which I'm writing now. And you should be able to follow along. So yeah. So now we sort of need to prove this claim 1 that each of the components of G minus V will have at least two edges of to V. And this I'm claiming this sort of, and this what I'm saying is this sort of claim is easy to show. Why? Because every vertex. So here, so till now we have not invoked this property, right? That every vertex has even degree, right? And now we'll be invoking this problem. So yeah. Yeah. So now to prove this claim, we'll be sort of invoking this property that if every vertex has an even degree, each of the components will have at least two edges to it. So now we'll sort of need to use this property that each vertex has an even degree. So, and how can we show this? So how do we prove? Prove by contradiction. We do prove by contradiction. And what's the proof by contradiction here? So we know that we need to have at least one edge to the component, right? Otherwise, the graph would not have been connected at all initially. So suppose we had only one edge to a component C. Let's say to the component C, we had only one edge. But we also know that but we know that every vertex of C has an even degree, right? Every vertex of C had an even degree, we sort of know. So now if we look at the graph, so we sort of know that every vertex of C has an even degree. And we also know that V has only one edge to the component C, right? So now maybe we can look at the graph of this component C and including V in that. So if we look at the graph, uh, C, maybe so if we look at the graph C prime, which is equal to C union V, then we can sort of see. So basically, we had this component C, right? Now, if I add the vertex V to this component C, in this graph, we can sort of say that then in C prime, V has a degree of 1, but all other vertices have an even degree. So I hope this sort of statement is clear to everyone that every vertex of C had an even degree and we only had one edge to the component C. We assume this for proof by contradiction, right? So now if we look at the graph of, let's say, the C prime, which is C union V, then in this C prime graph, we will have a degree of 1 because we had only one edge to the component C, but all other vertices will have an even degree because every vertex of G had an even degree, right? And we know that no two components have an edge between each other because otherwise they would have been a single component anyways. So yeah. So basically in this graph C prime, we have one vertex which has degree 1, but all other vertices have an even degree. So this is a contradiction. And why is it a contradiction? Because of the handshaking lemma. And what is handshaking lemma? This handshaking lemma was discussed in the lectures also, I believe. As handshaking lemma says that in any graph, there should be an an even number of odd degree vertices. So the number of odd degree vertices, like there should be an even number of odd degree vertices in any graph. But we see that in this graph C prime, only V has an odd degree, which is degree 1. But all other vertices have an even degree. So the number of odd degree vertices in C prime is 1, which is V, which is not possible because by handshaking lemma because there should be an even number of odd degree vertices. So this is why we obtain sort of a contradiction. Yeah, odd degree. So this is why we obtain a contradiction, and hence each of the components will have at least two edges to V. Each of the components of G minus V will have at least two edges to V. And so if we have proved this, then this claim 2, as we had initially said, that claim 2 is trivial if claim was true. So we have sort of proved that number of components will be actually less than equal to D. For any general connected graph, number of components will be less than equal to 2D. But for special graphs where every vertex also has even degree, the number of components will be actually less than equal to D. So what's the option here? Like cannot exceed D is the option B here. So this will be the final answer, that it cannot exceed D. So hence option B is correct. So note that even though it was an MCQ, but yeah, it involved some good claims and stuff like that. So this is a good practice for you guys. So hence option B is correct. Yeah. Okay, so let's come to the last question for the day then. So this last question is again consisting of multiple options, but yeah, I believe it's a bit straightforward. That so we are again given a simple graph G, V, comma E, and we need to select the correct statements. So the first statement says that an edge E belong to the edge set is a cut edge if it does not belong to any cycle in G. So note that what's an edge cut and what's a cut edge. Maybe I should write down these definitions also. So what's a cut edge? Cut edge. So these notions of cut edges and stuff like that are and vertex connectivity are defined for connected graphs. So an edge E is a cut edge in G if deletion of E disconnects G. So if deleting that edge results in the disconnection of G, which was initially connected, then that edge E is a cut edge. So note that if there exists a cut edge in a graph, then edge connectivity of that graph is actually equal to 1, because edge connectivity is nothing but minimum size subset of edges which need to be deleted so that G become disconnected. We know that this should be at least 1 because G was initially connected. This value should be at least 1. And if there exists a cut edge, then this value is exactly equal to 1. So in graphs where cut edge exists, this cut edge need not exist for every graph, right? But in graphs where the cut edge exists, the edge connectivity is also equal. So an edge E is a cut edge in G if deletion of E disconnects G. Similarly, what's an edge cut? Similarly, we can define the notion of cut vertex also, like deleting that vertex disconnects the graph. Like, you can extend all the notions of edges to vertices also. Similarly, what's an edge cut of a connected graph G? So note that these are two different things. Like earlier I defined a cut edge. Now I'm defining an edge cut. Edge cut is nothing but a subset of edges, of G, basically, whose deletion results in whose deletion disconnects G, basically. So a subset of edges whose deletion disconnects G is edge cut. So basically, a cut edge is actually an edge cut of size 1, because a cut edge is nothing but a single edge whose deletion disconnects G. An edge cut is just a subset of edges which, when deleted together, disconnect G. So note that there can be multiple cut edges, there can be multiple edge cuts in a graph and stuff like that. So yeah. So a very trivial edge cut for a graph is just the whole edge set. If we delete all the edges of the graph, then that graph is trivially disconnected, right? So yeah. So edge cut is just subset of edges whose deletion disconnects. So let's just come to this question after we have discussed these definitions. So let's just go option by option here. So option A says that an edge E is a cut edge if it does not belong to any cycle in G. So yeah, actually this statement is correct. And you can sort of see this lectures also, like I'll not write down the whole argument because these sorts of claims have already been discussed in the lectures, but I'll just give a high level idea again. So an edge E is a cut edge if it does not belong to any cycle of G. And why is it true? So suppose the edge actually belong to a cycle in G. So even after deleting that edge E, uh, all the vertices of the cycle still remain connected, right? So what this essentially means is that all the vertices of the graph still remain connected. So that's why E can't be a cut edge if it belongs to some cycle. So E is a cut edge if it does not belong to any cycle. So yeah, an edge E is a cut edge. Note that here they are given if statement only, but it's a strongest. Like I am saying that there's a strong statement that edge is a cut edge if and only if and only if it does not belong to any cycle in P. So yeah. So actually both sides are true. Like if the edge does not belong to any cycle, then it's a cut edge. And if it's a cut edge, then it does not belong to any cycle. So yeah. So option A is correct. So option B says if for all edges E belongs to a cycle in G, then G does not have an edge cut. So this statement says that if for all edges E belongs to a cycle in G. So actually what this statement means is that if every E belongs to a cycle, then like no edge can be a cut edge, right? Like because for a cut edge, as I defined previously also, it is a cut edge if and only if it does not belong to any cycle. But here in the option B, it's saying that if all edges belong to some cycle in G, so then it essentially means that the graph G does not have any cut edge, right? If all edges belong to some cycle, then no edge can be a cut edge in that graph. So that sort of claim is okay. But here they are not talking here they are not talking about cut edges, but rather about edge cuts. So you need to be careful with this terminology as it can be a bit confusing and can lead to incorrect answers. So G will not have any cut edge. This we have established easily. But they are saying that G will not have an edge cut. This is incorrect. Like this claim is incorrect because as I told you previously also, a very trivial edge cut is just taking out or deleting all the like edge cut is just a subset of vertices whose deletion disconnects the whole graph. So yeah, so if we select all the edges of the graph, then that will trivially form an edge cut. So almost all the times there will always exist an edge cut in a graph. There may be times that there may be instances in which there does not exist cut edges, but an edge cut will always exist. So option B is incorrect. As the set of all edges is a trivial edge cut. Still a trivial edge cut, right? So option C says that suppose G has an edge connectivity of 2. And what does edge connectivity mean? The minimum subset of edges such that their deletion results in disconnection of the graph G, right? So if E1, E2 is an edge cut for some E1, E2 belonging to E, so note that G has an edge connectivity of 2 and E1, E2 is also an edge cut. And E1, E2 is just a size 2 cut set, right? It's a size 2 set. So actually this E1, E2 is one such set which gives us this edge connectivity of 2 here. So yeah. So if E1, E2 is an edge cut for some E1, E2 belonging to E, then E1 and E2 lie on a common cycle in G. So the claim is that if the graph has an edge connectivity of 2 and E1, E2 is an edge cut, so E1, E2 is an edge cut, this means that deletion of E1, E2 disconnects G. Then E1 and E2 should lie on a common cycle in G. So I believe these sort of arguments you should try, like basically option C and option D are just negations of each other. Like option C says that E1 and E2 should lie on a common cycle. Option D says E1 and E2 should not belong to a common cycle. So I just want to point out, maybe you should try it yourself, like option C and option D. Uh, like which of these is correct? Because this is something which has been sort of straightforward discussed in the lectures, uh, in some manner, the other. Because like similar arguments I've also discussed, like why does NEH belong to a cycle? Why does NEH cut edge does not belong to a cycle, and so on. So you can do this yourself. So I'll just give you the answer for this, and the answer for this is, so if E1 E2 is a cut edge for some E1 E2, then E1 E2 should actually lie on a common cycle. Like option C is actually correct, that E1 and E2 should actually lie on a common cycle. So one trivial way in which you can see is, let's just take some cycle graph. So a cycle graph has an edge connectivity of 2. And if a subset of two edges is an edge cut in that graph, then those two edges are trivially lying on a cycle, right? That's an example where option C holds, but option D does not hold. And option C holds in general for every graph. Like you can try to show this yourself, it won't be too difficult. Because if the graph has an edge connectivity of 2, deleting just E1 won't result in disconnection of G. Similarly, deleting just E2 won't result in disconnection of G. E1 and E2 both should together be deleted to result in disconnection of G. And so like it can be sort of easily seen that E1 and E2 should lie on a common cycle. Correct. Right. Yes. So I've given you some intuitive idea, but you should try to prove this yourself. And option D is incorrect. And the reasoning for this is like, as option C is correct, so option D will be incorrect. So yeah, try to prove this option C by yourself. Let's prove this. So yeah. So yeah, I guess the correct answer here will be option A and option C. So option A, option C are correct here. So yeah. So yeah, these are the 4 questions which I had for the day. So I guess this is it. So and this option C is something which I have not discussed, because I believe that you can prove this yourself. So if there are doubts in if you are not able to prove this, the correctness for this option C, you can always ask in the next doubt session, or you can ask on the NPTEL forum also. So yeah, so I guess this is it for the day. And like, so no one is in the session right now, but whoever's watching on YouTube. So thanks a lot for watching the session. So I'll be stopping sharing my screen and like stopping the recording now. So yeah. So hopefully we'll see you guys in person next week. Yeah. Same time next Tuesday, 6 to 8. So yeah. Thanks for watching the session, guys. Bye bye.